Ever designed a communication bus only to watch your signal drift off the baseline until the data is totally corrupted? Yeah, it's a nightmare. Welcome to this explainer. Today, we're decoding the 4B3T line code and finally solving that massive headache, signal drift.
Here is how we're going to tackle this. We'll start with beating DC bias, break down the 4B3T concept, go over the rules, run through a mathematical walkthrough, look at the accumulator track, and wrap up with key takeaways. Let's dive in. First up, beating DC bias. Picture the thousands of microcontrollers firing off inside a modern car. We send ones and zeros using electrical voltage. But there's a trap here. If you send too many positive voltage pulses in a row, this unmanaged DC voltage component, what engineers call the Gleichspannungsanteil, starts building up on the wire. Your baseline voltage literally drifts away from zero. It distorts the signal so badly that the receiver eventually can't tell a 1 from a 0 anymore. So how do we actually stop this signal drift in these ultra-sensitive networks? We absolutely need a way to send data while guaranteeing the average voltage always returns to 0. By the end of our time together today, you'll know exactly how the 4B3T code uses ternary signals to pull this off. Moving right along to the core concept, the 4B3T code. The name itself gives away the secret. It takes 4 standard binary data bits, your everyday ones and zeros, and maps them into a sequence of 3 ternary or 3-level voltage states, negative, 0, and positive. The whole goal, making sure your transmission is completely DC-free. To really lock this in, I want you to picture a playground seesaw. The total DC voltage on your network cable, that's the balance of the seesaw. Every positive ternary symbol you send is like dropping a heavy weight on the right side. The seesaw tips. To stop it from slamming into the ground, which means total signal corruption, you eventually have to send a negative symbol to drop a weight on the left side, pushing it back to a perfect 0-volt balance. And the 0 symbols? They don't add any weight at all. Your one job as the sender is to constantly keep that seesaw perfectly balanced. Okay, let's look at the rules behind this. Tables and ternary. We've got 2 main engineering standards to follow here. First is Table 2.7. This table handles inherently DC-free sequences. Check out the data sequence 1, 0, 1, 1. It maps straight to the ternary sequence, plus, 0, minus. Think back to our seesaw. You add a weight to the right with a plus, do nothing with a 0, and immediately add a weight to the left with a minus. They cancel each other out instantly. This seesaw stays perfectly balanced at a net 0 DC voltage. But then we hit Table 2.8, which shows 10 data combinations that are not naturally balanced. Take the data sequence 0000. You don't just have one mapping here, you've actually got 2 choices. You could send plus 0 plus, which tips the seesaw heavily to the positive side, or you could send 0 minus 0, tipping it negative. On their own, neither of these is balanced. So how on earth does the hardware know which one to use? Enter the balancing rule. The sender uses an internal accumulator to keep track of the historical voltage shift. Basically, it remembers the current tilt of the seesaw. If the seesaw is currently tilted positive, the hardware deliberately picks the negative mapping to pull it back down. It's constantly choosing the opposite polarity to maintain that perfect equilibrium. Let's put this into practice with a quick mathematical walkthrough. Step 1. Let's say we need to send the binary data 1011. We look that up in Table 2.7, and it gives us the naturally balanced mapping of plus 0 minus. Since the plus and minus cancel out, our running accumulator stays right at 0. Net 0 DC offset. Easy enough, right? Step 2. Now we want to send 0000. We find this one in Table 2.8, which means we have to make a choice. Right now, our accumulator is sitting at a neutral 0. Because we're neutral, the protocol lets us grab the positive mapping, plus 0 plus. We send those ternary symbols down the wire, but here is the crucial part. Our internal accumulator tracks that shift. It now knows the seesaw is currently tilted up on the positive side. Step 3, finally we send 1100. Table 2.8 gives us 2 options again, plus 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 or minus plus minus. We check our accumulator. Remember, we left it shifted in the positive direction. So the strict rules of 4B3T dictate we must choose the negative mapping, minus plus minus. By doing this, we pull the seesaw right back down to equilibrium and eliminate that DC component. That right there is the absolute magic of 4B3T in action. Now let's talk about the gotcha, the accumulator track. Unlike those naturally balanced words that don't require you to remember anything about the past, those 10 combinations from Table 2.8 totally depend on historical context. The output for sending 0000 isn't just some static code. It dynamically changes based on exactly what happened milliseconds prior.
And this is the massive pitfall that trips up so many engineers. If you're building a system or writing a script for this, and you forget to carry over that accumulator history from the previous bits, the whole thing falls apart. If your logic just defaults to the positive mapping every single time, your seesaw tips over immediately. The DC bias builds up, baseline wander kicks in, and suddenly your crisp signal degrades into total unreadable noise. You absolutely must track the past state.
All right, let's wrap this up with 3 key takeaways.
Number 1, 4B3T maps 4 binary data bits to 3 ternary levels, negative, 0, and positive. Number 2, never ever forget the seesaw. The entire protocol exists to maintain 0 DC bias by balancing those voltage weights. And number 3, Table 2.7 gives you the naturally DC-free combinations, while Table 2.8 forces the sender to actively track the accumulator history.
Think about the real-world stakes for a second. If you fail to perfectly track and balance that seesaw, an unchecked DC bias could literally crash an entire vehicle's communication system while it's driving down the highway. Understanding the physical layer isn't just some academic theory, it's absolutely critical for safety. I hope this explainer made the 4B3T code click for you. Hit subscribe for more engineering survival guides, and I'll catch you in the next explainer.